Welcome, everyone. Let's just jump right into it. Today, we are undertaking a complete masterclass on the physics of movement. I'm going to be guiding you through this explainer just like an expert teacher preparing you for your Class 9 school tests and, honestly, even those tricky entrance exams. We're going to break down absolutely every concept, from the fundamental basics of position all the way to the advanced mechanics of circular motion. My goal is to make sure you have the exact problem-solving scaffolding you need to absolutely ace your exams. So here is our roadmap for today. We're covering 1. Reference points and motion, 2. Distance versus displacement, 3. Speed, velocity, and acceleration, 4. Decoding motion graphs, and finally 5. Equations and circular motion. Let's get started. Starting off with Section 1, Reference points and motion. Okay, so before we can measure how something moves, we need to know exactly where it is, right? To specify where an object is, we have to start somewhere. That somewhere is what we call the reference point, or the origin. Think about a broken scale. If your ruler snapped in half and the 0 mark is just gone, you might place the start of your line at the 5 centimeter mark and end it at the 10 centimeter mark. You know the actual line is just 5 centimeters long, not 10, because your reference point shifted. Where you start observing entirely defines the values you measure. So if you ask yourself, can a position exist without an origin? Well, no, it's literally impossible. Now, here's a really fascinating truth about relativity. Motion entirely depends on your point of view. If the position of an object changes with respect to its reference point over time, it's in motion. If it doesn't, it's at rest. So think about it. Are you actually at rest right now while watching this explainer? Well, relative to your desk or the room you're sitting in, you are perfectly at rest. But if an observer were looking at you from outside the Earth, relative to the sun, you and the whole room around you are zooming through space. It all depends on your reference point. Moving right along to Section 2, Distance versus Displacement. This is a classic exam favorite, so pay close attention. Distance is a scalar quantity, meaning it only cares about the total path covered. Displacement, on the other hand, is a vector quantity. It needs both magnitude and direction, and it represents the absolute shortest straight line between the starting and ending points. Consider a highly testable example. Usha swims from one end of a 90-meter pool and back. Her total distance covered is 180 meters. But because she returned exactly to her starting reference point, her initial and final positions are completely identical. Therefore, her displacement is an absolute 0. Here's a quick conceptual test for you. Can distance ever be 0 if an object has actually moved? No way, never. All right, Section 3, Speed, Velocity, and Acceleration. So we know where an object went and the path it took, but now we need to figure out exactly how fast it got there. Speed is simply the distance traveled per unit time. When you look at a car's speedometer, it's literally telling you the speed. But velocity is displacement for unit time. It's speed with a specific direction attached to it. Both share the vital SI unit of meters per second. So the crucial takeaway here is that if your direction changes, even if your speedometer stays perfectly steady at, say, 50 kilometers per hour, your velocity is technically changing because the direction parameter of the vector has shifted. And when velocity changes, we get acceleration. It is the rate of change of velocity over time. The formula you absolutely must memorize for your exams is A equals V minus U, all divided by T. Let's decode those variables. V is your final velocity, U is your initial velocity, and T is time. The SI unit is meters per second squared. Also, remember, if an object is slowing down, that means the final velocity is lower than the initial, which gives you a negative acceleration. In physics, we call this retardation. A super common exam mistake is forgetting to add that negative sign for retardation, so definitely watch out for that. If you see this type of numerical in an entrance exam, don't panic. It looks a bit tricky because of the units, but let's break it down using our standard step-by-step scaffolding. The question is, a car accelerates uniformly from 18 kilometers per hour to 36 kilometers per hour in 5 seconds. Calculate the acceleration. Okay, a massive, and I mean massive, mistake students make here is forgetting to convert kilometers per hour into meters per second before doing the actual math. To convert, you use this neat little trick. Simply multiply by 5 over 18. So let's take our time. Our initial velocity u of 18 kilometers per hour multiplied by 5 over 18 becomes 5 meters per second. Our final velocity v of 36 kilometers per hour becomes 10 meters per second. Now, just apply the formula. 10 minus 5 is 5, divide that by our time of 5 seconds, And boom, our final answer is an acceleration of 1 meter per second squared. Always, always check your units first. Next up, Section 4, Decoding Motion Graphs. Visualizing data is highly testable. In fact, many advanced questions won't even give you numbers directly, they'll just give you a picture. So let's unlock the secrets hidden inside kinematics graphs. First up is the position time graph. Time is always on the x-axis and position is on the y-axis. The most important thing to know here is that the slope, meaning the steepness of the line, tells us the velocity. When you look at the steepest upward line here, ask yourself, what does that actually mean? It means a higher velocity. Steepness directly translates to speed. A steeper line simply means the object is moving faster. You'll want to memorize these 3 shapes because examiners love asking you to identify the state of motion from just a quick visual glance. First, if the line is perfectly flat and parallel to the time axis, the position isn't changing. The object is at rest. Second, if it's a straight diagonal line, it's covering equal distances in equal intervals of time. That's uniform motion or constant speed. Finally, if the line is curved, the slope itself is changing, which means the speed is changing. This represents non-uniform accelerated motion. Next is the velocity time graph. Here, the slope represents the rate of change of velocity, which, as we know, is acceleration. But there is a hidden superpower in this specific graph, the area under the curve. Finding the area of the rectangle or triangle under a velocity time graph is the ultimate shortcut for calculating total distance on a test. Notice the trick here. A flat horizontal line on a velocity graph means you are still moving just at a constant speed, meaning 0 acceleration. Contrast that with the position graph we just saw, where a flat line meant you were completely stopped. See the difference? An upward straight diagonal line here means uniform acceleration. A downward straight line means uniform retardation, kind of like hitting the brakes smoothly. And a curved line means non-uniform acceleration. And here we are, Section 5, Equations and Circular Motion, the final boss. We've reached what is arguably the trickiest conceptual hurdle in the chapter, the kinematic equations. Take a mental screenshot of this slide. For motion in a straight line with constant acceleration, these 3 equations are your absolute ultimate toolkit for solving almost any motion numerical. The key to exams is simply knowing which one to pick. If the question gives you no information about distance, use the first equation. If you need distance and you have the time, use the second. If you don't have the time parameter at all, the third equation is your go-to. Let's move to a direct application and see how this builds our problem-solving muscles. Read the question carefully and look for the hidden variables. It asks, a racing car has a uniform acceleration of 4 meters per second squared. What distance will it cover in 10 seconds after start? The secret clue in the question was the phrase, after start. This immediately tells an expert student that the initial velocity, u, is absolute 0. We're given acceleration a is 4 and time t is 10. We need distance s. We have time, so we select the second equation, s equals ut plus half at squared. Since u is 0, that entire first ut term just vanishes. We're left with 1/2 times 4 times 10 squared. Half of 4 is 2, 10 squared is 100. 2 times 100 gives us a final distance of 200 meters. Simple, logical, and highly effective. Finally, let's tackle uniform circular motion. Imagine an athlete running around a circular track at a perfectly steady speed. The speed is uniform, right? But remember, velocity is a vector. It requires direction. Because the circular path forces the runner's direction to shift at every single microsecond, the velocity is continuously changing. And since a change in velocity over time is the literal definition of acceleration, uniform circular motion is always considered an accelerated motion, even if the speedometer never moves. Okay, as we wrap up this explainer, let's lock in our final revision notes before your test. These are the exact traps and common misconceptions exam setters use to deduct points. Distance will always be greater than or equal to displacement. Displacement can absolutely be 0 if you return to the start. Always, always check your units and use the 5/18 trick. Remember the circular motion exception, and never forget that the area under a velocity time graph equals distance. We have covered a tremendous amount of ground today, from the relativity of a simple reference point to the math behind acceleration. So I'll leave you with this to ponder. If you are spinning on a playground merry-go-round at a perfectly constant speed, you are in uniform circular motion. You are constantly accelerating. But what invisible force is actually pulling you to cause that continuous change in direction? Think about that next time you spin, and keep exploring the incredible physics governing our everyday world. Good luck on your exams.